Next topic is one so important, even the president in the West Wing is talking about it. That of table salt.
I've been seated next to a chemist tonight.
Mullis?
23 Nobel Prize winners in the East Room. I couldn't get literature or, I don't know, peace or something?
What's her problem?
She thinks she won't be able to make conversation with the guy, but she's wrong because she knows what year he was born and his name.
You gotta be a cryptographer. They speak in combinations of letters that don't spell anything but end up meaning table salt.
Mr. President?
Is it here?
Yes, sir.
Okay. Hey,
Good evening, Mr. President.
what's your name?
I'm Donald Dolan from the Office of the Executive Clerk, sir.
Leo, I don't think it's a bluff. I don't think the congressional leadership holds their members back on a weekend for a bluff.
I don't think they're bluffing, Sam.
You think they're holding an override vote tonight?
I'm sure of it.
Why would they hold a vote if they didn't think they could override?
They wouldn't. What do you got in the box, Mr. Dolan?
Mr. President, I have House Resolution 10, the Death Tax Elimination Act. It bears the signatures of both the Speaker of the House and the President of the Senate, and it's presented to you by the Congress of the United States for your signature or veto.
Excuse me. Leo, you think we lost some votes we don't know about?
I think we're about to find out.
Sir, if the House successfully overrides the veto, we're gonna look weak.
If the House successfully overrides the veto, we are weak. NaCl, CJ.
I'm sorry, sir?
Table salt. Send it back.
Okay, let's talk about ionic compounds. We've talked about positively charged ions, such as sodium, and we've talked about negatively charged ions, such as chloride. An ionic bond is simply the force of attraction between two ions of opposite charge. That's right. Ionic bonding simply boils down to the simplest, oldest, fundamentalist rule in the universe. Opposites attract. Sodium has the charge opposite of chloride, so it's attracted to chloride. Chloride has a charge opposite of sodium, so it's attracted to sodium. Matter of fact, the attraction between sodium and chloride causes it to form the compound known as sodium chloride, which we know by its more common name of table salt. Table salt, or sodium chloride, is also the perfect example of the different properties that ionic compounds have. All ionic compounds have high melting points and high boiling points. After all, when was the last time you were cooking and worried about salt melting, right? When was the last time you saw salt boiled? Very extremely high melting points, very extremely high boiling points. Therefore, ionic compounds are nearly exclusively solids at room temperature. And those are your important characteristics of ionic compounds. In addition to table salt, we are also really into ionic compounds as a society. Most of your gemstones are actually ionic compounds. For example, sapphires and rubies are ionic compounds that contain aluminum and oxygen. And usually they'll have one other metal in there somewhere in the matrix that gives them their slightly different color. For example, chromium, forming an ionic compound with aluminum and oxygen, makes rubies red. Iron and titanium make sapphires blue when they're combined with the aluminum and the oxygen. So we see ionic compounds in nature. Let's take a close look at table salt. And by a close look at table salt, I mean, let's take a look at one of those little grains. If you look at one of those little grains and kind of roll it around in your fingers, you'll feel it's hard. That is actually a crystal of table salts. salt. Ionic compounds Ionic compounds exist as crystals, not as molecules. What? What do we mean by that? What's a crystal? Let's zoom in on our little picture here. A crystal is a regular repeating three-dimensional pattern of particles. Why do ionic compounds exist as crystals? After all, how do they differ from a molecule? It has to do with the nature of an ionic bond. We said that ionic compounds were held together by the force of attraction between the positively charged ion and the negatively charged ion. Well, some of you, like me, bear the burden of being unbelievably attractive. And you know that there's no way to control your attractiveness, right? There's no way you can say, I just want to be attractive to that one person over there. No, it's impossible. I mean, you're so unbearably attractive like I am that everybody you meet's attracted to you, right? You just can't help it. It's the same way for our ions. Our sodium can't say, I'm going to take this positive charge and I'm going to aim it like a gun over here at just the one chloride ion. No. That positive charge of attractiveness goes in 360 degrees in three-dimensional space. And that sodium ion is actually going to attract as many chloride ions as can physically fit around it. Oh, but don't worry. The sodium ion's not the only dog in the ionic world. These chloride ions are playing the field as well. These chloride ions, they can't aim who they're attracting. And they're going to attract as many sodium ions as can fit around them in three-dimensional space. So what happens in a crystal of table salt, even though we write the chemical formula, for table salt as sodium chloride, never ever in nature will you find one sodium ion and one chloride ion. It's not going to happen. It's not going to be found that way. You're not going to find just one sodium ion and one chloride ion. Instead, you're going to find thousands and billions and trillions of sodium ions attracted to billions and trillions of chloride ions. So if that's what's occurring, why do we write the formula one sodium and one chloride? The formula The formula for an ionic compound represents a ratio. It represents the ratio of ions in the crystal. In other words, even though that crystal of table salt that you're holding in your hand consists of trillions of sodiums and trillions of chloride, if we were to count all those sodiums and count all those chlorides, we discover that for every one sodium we had, we also had one chloride. Okay, so the chemical formula of an ionic compound represents the elemental symbols and subscripts which represent the lowest whole number ratio of the ions. In other words, a chemical formula represents the ratio of the ions in the crystal. Now, ionic compounds always form so that the sum of the positive and negatively charged ions is always equal to 0. In other words, the total positive charge is always going to equal the total negative charge. For example, calcium's a group 2A element, so it forms a +2 cation. Chlorine is a group 7A element, so it forms a -1 charge. If these two are going to form a compound, they would form one where their charge is canceled out. And since my calcium has a +2 charge and my chlorine a -1 charge, I would need 2 chlorines to cancel out the charge of my calcium. That would make my formula 1 calcium and 2 chlorines. Chemistry's easy, life is hard, yes? One last important thing to note when writing the formula for an ionic compound, the symbol for the metal is always written first, followed by the symbol for the nonmetal. So it's always going to be metal, or your positive ion, followed by the symbol for your nonmetal, or your negative ion. And you're saying, wait a second, can those contradict? No. Metals always form positive ions, nonmetals form negative ions. So it'll always be metal, nonmetal, or positive, negative. Why don't you write down Taft? Everybody write down Taft. T-A-F-T. President Taft. All right. Let's kick our ability to test ourselves on predicting what ionic compounds would form up a little bit. What compound would magnesium and chlorine form? To answer this question, you're going to do a couple easy things. First, you're going to identify your ions using the periodic table. So first of all, I'm going to find magnesium on my periodic table. I come up here, I look for magnesium, and I find magnesium right there. Magnesium's in group 2A. Well, I know since magnesium's in group 2A, and anything in group 2A forms a +2 ion, so I know one of my ions is magnesium plus. Now I have to figure out what ion chlorine's going to form. I come over here and I locate chlorine. Chlorine's in group 7A, and I know anything in group 7A forms a -1 ion. So I know my ion from chlorine is going to be a -1. So I've identified my ions. My next step is going to be to balance my charges. Magnesium has a +2 charge. Chlorine has a -1 charge. So if I have a +2 charge, I need a -2 charge to cancel it out so that they will sum to 0. So I'm going to need 2 chlorines so that my total negative charge is 2 negative to counteract my +2 charge. So I'm going to have 1 magnesium and 2 chlorines. And I denote the fact that I have 2 chlorines by writing a 2 as a subscript down here. Notice my charges don't show in my final formula. That's it. Chemistry's easy, life is hard. Let's take a look at another example. What compound would form between sodium and nitrogen? Same steps. 1. Identify your ions. So I'm going to go to my periodic table, and I'm going to locate sodium, and I see right there sodium. It's in group 1A. I know anything in group 1A forms a +1 ion. So one of my ions is sodium plus. Now I need to find my nitrogen. My nitrogen is over here in group 5A. Remember that we singled out nitrogen and phosphorus in the last lecture as being special. We said that nitrogen and phosphorus were the only 2 nonmetals in group 5A and that they both had charges of 3 negative. You have no problem remembering nitrogen and phosphorus have 3 negative charges. So our ions are sodium +1 and nitrogen 3 negative. Now, whoops. Well, that didn't go like I wanted it to. Now we need to balance those charges or get them to cancel out. We have a -3 charge on sodium. We have a +1 charge on sodium, a -3 charge on my nitrogen over here. I need to get those charges to cancel out. So if I have a -3 here, I'm going to need 3 sodiums so that I have a net positive charge of +3 to cancel out the -3 on my nitride. I would write that by taking my sodium, putting a 3 as a subscript so that I have 3 sodiums, and then my 1 nitrogen. And there you have sodium nitride. All right, let's see if you have the hang of it. See if you can come up with the correct formula for the following 3 combinations. Pause me, seriously, pause me. Pause me and try this yourself. Are you pausing me? Did you pause me? Oh, come on! Please pause me. Did you pause me? I'm extending you some trust here. Let's take a look. First of all, what compound would we get from sodium and sulfide? Sodium has a +1 charge, sulfide has a 2 negative charge. So I'm going to need 2 sodiums to cancel out the 2 negative charge on my sulfur. So I would say that I have 2 sodiums and 1 sulfur in my compound, or B. Now let's take a look at our aluminum at +3 and our chloride at -1. I'm going to need 3 chlorines so that my total negative charge is -3 to counter the +3 charge on my aluminum. So I'd write the formula, aluminum and 3 chlorides. Choice A. This last one is really, really tricky. Let's take a look. We have magnesium with a +2, and we have nitrogen with a 3 negative. Is there any amount I can raise 2 to get the same thing as 3, or 3 the same thing as 2? No. So we'd have to do what's known in math classes, looking for the least common multiple. Both 3 and 2 can go into 6. So what I would do is I'd say, okay, if I have 3 magnesiums, I would have a total charge of 6 positive. And if I have 2 nitrides, then I'd have a total negative charge of -6. And then my charges would cancel out. So my chemical formula would be Mg3N2. Now you're saying, wait, least common multiples? Wait a second, Dr. Kelly, you promised us a low content math class. Keeping the word. I mean, low math in this class. We will. There's an easier way to do this than searching for that least common multiple. When something's not obvious, like it is with your aluminum chloride, where you've got 3 to 1 or 1 to 2, there's an easy way to go about it. The easy way to go about it goes like this. You can do what's known as crisscrossing the charges. Make the charge of one ion the number of the other ion. Make the charge of the other ion the number of the other ion. In other words, because magnesium is +2, I'm going to have 2 nitrogens. Because nitrogen is 3 negative, I'm going to have 3 magnesiums, otherwise known as the crisscross method. Getting up and jumping around is completely optional. And you can see how your crisscross method works, because once again, you wind up with 3 magnesiums, Mg32, 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 or a total charge of +6, and you have 2 nitrogens, each with the -3 charge, so a total negative charge of 6 negative. So crisscrossing is an easy way to solve that math problem. Crisscrossing even works for those simple ones up here, right? I have sodium +1 up here, so I'd have a 1 down there for my sodium, a 2 there, so I'd have a 2 down there for my sodium. So crisscrossing is an easy way to solve for the formula of ionic compounds.